Welcome back to the deep dive, where we really try to get into some of the more complicated, more interesting, and frankly, more useful AI research papers that are out there.
Hmm.
And today, we're diving into the DIFF Transformer.
Yeah, this is a really interesting one. It's a new architecture, and as we'll see, it kind of addresses some of the shortcomings of traditional transformers.
And it's tackled, I think, in a really elegant way.
Yeah.
So the paper itself, which is called Differential Transformer, jumps right into a problem that anyone who's ever worked with large language models knows all too well.
Yeah.
Attention noise.
Mm-hmm.
It's like trying to drink from a fire hose of information.
Yeah.
These models are just bombarded with so much data, and sometimes they end up focusing on, well, the spray instead of the actual stream of useful information.
Yeah, I like that analogy. It's very visual. And you know what's interesting is that a lot of approaches to solving this problem, they try to kind of filter out that noise. But the DIF transformer, it takes a different approach. It uses this differential attention mechanism that actually changes how the model decides what is and is not important.
Differential attention. I gotta say, that phrase, when I first read it, it really caught my eye. It just hints at something a lot more nuanced than just like turning up the volume on the important stuff. It's like the model is actually performing some kind of, I don't know, signal subtraction
Yeah.
to really isolate what matters.
That's a great way to put it. Imagine you have two attention heads that are both looking at the same information, right? One of them is working kind of like a traditional transformer, looking for statistically prominent features and that kind of thing. But the second one, that's where things get really interesting.
Okay, I'm hooked. Tell me more about this second attention head. What's it doing that's so special?
So the second attention head, what it's designed to do is capture what the authors of the paper call common noise. Basically, these are the elements in the data that are statistically salient. So they stand out to the model, but they're not actually relevant to the context. And these are the things that often lead to that attention drift that you see in traditional models.
Okay, so I'm starting to see where the differential part comes in. It's almost like they're applying a noise-canceling algorithm, but instead of sound waves, they're doing it with the attention mechanism itself.
Exactly. They're taking the attention maps generated by these two heads, and they're subtracting one from the other. And what you're left with is a much clearer representation of the information that is truly distinctive and important in that specific context.
So by subtracting that common noise, you're essentially forcing the model to focus on what really differentiates the relevant information from everything else.
Right. It goes beyond simple statistical significance. The model has to figure out what's really important for understanding the meaning, for understanding the context.
And this, I'm guessing, is where we see those really impressive gains in efficiency and performance, especially when it comes to things like long context modeling, where those traditional transformers tend to, lose their way a little bit.
Exactly. Because it's so good at zeroing in on those really salient features, the DIF transformer can achieve comparable, sometimes even better performance than the traditional models, but it does it with significantly fewer parameters and less training data.
Okay, now you're talking my language. That's a huge deal, especially when you think about the amount of compute power and resources that go into training these massive models.
It really is. This differential attention idea, it's not just about making things more efficient. It's about approaching the problem of information relevance in a fundamentally different way. And it seems to be paying off.
So this differential attention mechanism sounds super interesting, but, at the end of the day, the real test, especially for our listeners who are deep in the trenches of ML research, is in the performance, right?
Yeah.
What are we seeing in terms of actual efficiency gains, accuracy improvements, that kind of thing?
Yeah, for sure. And the results are pretty impressive, especially when you look at long context modeling. I mean, that's always been a tough one for traditional transformers, but the paper shows that these DIF transformers, they can actually achieve comparable performance, sometimes even better, and they do it using only about 65% of the parameters and training data.
Wow, 65%. That's a pretty significant reduction in resource requirements. I'm sure anyone who's ever waited for a model to train is breathing a sigh of relief right now.
It's huge, really, not just for researchers who are, battling for compute time and storage space, but also for the field as a whole. I mean, This kind of efficiency gain could really open doors for more researchers, especially those with more limited resources.
And it's not just about computational efficiency either, right? The paper also mentions something about how this differential attention helps to reduce those, what do they call them, hallucinations, where the model kind of makes things up instead of sticking to the data it's been trained on.
Yeah, hallucinations. That's been a big challenge in language modeling, making sure these models stay grounded in reality. But it makes sense that the DIFF transformer would do better on that front because it's so focused on finding those really relevant contextual cues. It's less likely to get sidetracked by spurious correlations or extrapolate wildly from limited information.
So it's not just more efficient with computation, it's more efficient with information itself, which ultimately leads to more accurate and trustworthy outputs.
Absolutely. And this whole idea of focusing on contextually relevant information, it goes beyond just reducing hallucinations. It also plays a big role in the model's ability to learn from limited examples. We're talking about in-context learning here.
Right, in context learning. That's where the model can kind of adapt to new information or new tasks without needing to be completely retrained on a massive new data set. It's almost like you're showing the model a few examples and it just gets it.
Exactly. And here's the really interesting part. The DIF transformer, it doesn't just do well in context learning scenarios, it actually seems to handle variations in the order of information better than traditional transformers.
Order variations. You mean like if those examples were presented in a different sequence, why would that matter to a model that's supposed to be learning, abstract representations?
That's a great question. It turns out that traditional transformers, even though they're incredibly powerful, they can be surprisingly sensitive to the order in which they see information. It's like they develop this somewhat rigid understanding of the relationships between data points based on that initial order.
So they're kind of like, I don't know, learning by rote memorization instead of actually understanding the underlying concepts.
Yeah, that's a good way to think about it. They're very good at picking up on patterns, but those patterns are often tied to the specific sequence in which they were encountered. With DI transformers, on the other hand, it seems like they're developing a more flexible and adaptable understanding of those relationships.
Which would make sense, right? If they're focusing on the truly relevant information, the order it's presented in shouldn't matter as much.
Exactly. It suggests a more robust and nuanced form of learning, one that's less likely to fall apart when it encounters new or unexpected data sequences.
And that's obviously crucial for real-world applications where, let's face it, information is rarely presented in a perfectly predictable or consistent way.
Absolutely. This ability to generalize across different data arrangements, it's a big deal.
So we've got efficiency gains, we've got improved accuracy, we've got better handling of long sequences, and more robust in-context learning. Is there anything this DIF transformer can't do?
Well, it's not magic, but it is impressive. And there's one more thing I wanted to touch on, something that really caught my eye in the paper. This idea of activation outlier reduction.
Activation outlier reduction. Okay, now you're just using big words to sound smart. But seriously, I have to admit, I'm not familiar with that term. Break it down for me. What are we talking about here? Okay, activation outlier reduction. It definitely sounds technical, I'll give you that.
Yeah.
But I'm here to learn, so enlighten me. What are these activation outliers and why should we care about reducing them?
So imagine you're looking inside the model, right? You've got all these artificial neurons, and as information flows through the network, each neuron gets activated to a certain degree, like it's responding to the input. Now, an outlier in this context is basically a neuron that's maybe a little too enthusiastic. It has this unusually high activation level compared to all the other neurons. Like it's overreacting to something in the data.
So like that one friend who gets way too excited about a topic, even if it's not that big of a deal in the grand scheme of things.
Exactly. And just like with your friend, it's not necessarily a bad thing, but it can cause some complications, especially when you're trying to optimize these models for deployment.
I see where you're going with this. We're talking about things like model compression, quantization, all those techniques that are essential for getting these AI behemoths to run on devices that don't have, the processing power of a supercomputer.
Right. And those outliers, with their exaggerated activations, they can really throw a wrench in the works.
Because if you're trying to quantize a model, you're basically trying to represent those activation levels, those numerical values, using a smaller number of bits, right, to make the model lighter and faster. But if you've got these outliers with these huge values, it's like trying to cram a bunch of bulky furniture into a tiny moving van. It's just not going to fit well.
Perfect analogy. So by reducing these outliers, you're essentially smoothing things out, making the model more compact and efficient.
So it's fascinating to me how this would seem like a fairly subtle tweak to the attention mechanism, this differential approach, can have these ripple effects throughout the entire architecture, leading to all these practical advantages.
That's what I love about this kind of research, seeing how these elegant solutions can emerge from really fundamental insights. And the implications here are significant. This ability to reduce activation outliers could really open doors for deploying these powerful AI systems on a much wider range of devices.
It sounds like we've only just begun to scratch the surface of what DIFF transformers are capable of. From this really innovative differential attention mechanism to its impressive performance on long context tasks, and now this whole activation outlier reduction thing, there's a lot to be excited about. For our listeners who are eager to dive into the nitty-gritty, we'll be sure to include a link to the paper, Differential Transformer, in the show notes.
It's a great read, and I think it really highlights the direction that transformer research is heading.
Absolutely. Well, on that note, we'll wrap up this deep dive into the world of DIFF transformers. Until next time, keep those minds engaged. And remember, sometimes the most elegant solutions come from embracing a little difference.